My name is Chen and come from Sun University, and I'm pleased to share some recent advancement in the field of quantum cryptography. Uh, as we know, the looming threat of quantum computer is pushing serious risk to the classical cryptography. As a leading example of quantum information, quantum key distribution offer a complete solution. QKD is based on the fundamental principle of quantum mechanics, so it can achieve a communication with information theoretical security. And then, since the introduction of the first QAD protocol, BB84, over 40 years ago, the field has evolved remarkable. QKD have moved from theoretical fundamental to the real-world application, uh, enable not only satellite to ground, but also the development of various large-scale quantum network. And in current quantum network, the BB84 protocol has been widely adopted due to the simple structure, but its really real-world application is still face several problems. In the free space channel, such as the satellite to ground, the turbulence will cause the drift between X and Bob's reference frame. Similarly, the polarization will change over time due to the actual fiber channel. Therefore, a real-life QKD system need to perform a real-time reference frame computation. Fortunately, these issues are effectively addressed by the reference frame independent quantum key distribution, which allow the user work in an elegant reference frame. And then, alpha QKD has been successfully demonstrated across a variety of platforms, including the optical fiber, free space, and quantum network. Then it also has inspired several extended protocols, such as the R5 measurement device independent quantum key distribution, the R5 mode pairing quantum key distribution, and the R5 twin field quantum key distribution. But although the R5 QAD has been excellent application potential, its widely development is still hindered by several challenges. First, the R5 QAD protocol is more complex than the BB84 protocol. And secondly, the secondly, the requirement of the high precision synchronization increase the additional cost. So our proposal is to address this challenge and achieve a more practical RFID system. For the first challenge, to address the complexity of the RFID system, we propose a simple RFID protocol. It means, let me see the original RFID system. In this protocol, the Alice need to prepare quantum state in Z, X, and Y basis, and then Bob need to measure it in the Z, X, and Y. In this protocol, they need to operation of 6 quantum state. And in our protocol, it is the fourth state RFID system. In this protocol, the Alice only need to prepare the 4 quantum state and then Bob measure in the Z and back and X basis. And then we conduct a detailed performance evaluation of the four-state RFID system. The results show that compared to the original four-state RFID system, our protocol efficiently balancing the practicality its application and the performance. Now let me turning now the second challenge, the synchronization, which is a core component of the QKD system. Obviously, the need of high precision synchronization lead to increased additional hardware costs. Furthermore, the widely optical synchronization method will also include the additional crosstalk to affect the quantum set our protocol performance. So to overcome this limitation, the research from Italy proposed a qubit-based synchronization method that without additional hardware. And inspired by this, so we propose optimized qubit-based synchronization method, which is more stable and easy to re-synchronization. In this method, we periodically encode the synchronization sequence in a quantum signal, and then the synchronization by the quantum state. So without any additional hardware, by only use the quantum state. And then we successfully achieved our method in a polarization-based BB84 system with a frequency of 645 megahertz. And then we implement this method in a BB84 quantum network and successfully conduct a two-user experiment, further demonstrating the practicality of our synchronization method. So naturally, we hope to further application this synchronization method to the RFID system that are based on the time-beam encoding to reduce its hardware requirement to address the second challenge. But however, unlikely to the BBS4 protocol in a time-beam-based RFID system, the quantum state are distributed in three kind of time windows due to the path difference. This highlights the direct application of the organal qubit-based synchronization. So to overcome this challenge, we developed a machine learning enhanced qubit synchronization method. This method operates in two stages. The first, period recover, and the second, time offset recover. Our experiment setup is based on the four-state RFID protocol, where both adopt a fully passive measurement, and the protocol scan is showing left. In the period recover, we employed a machine learning based machine method based on the key nearest neighbor. This method can classify the detection in their respective time windows and extract the interference peak suitable for the period recover. So this inversion transforms the synchronization challenge to in the time-beam encoding RFID system into a problem that be solved by using the qubit-based method in a BB system. And then in the time of that recover, the bulb perform a correlation operation between the received quantum state and the public synchronization screen to confirm the detection used for synchronization. And then the bulb will calculate the time offset based on the position of the correlation peaks. So based on the machine learning enhanced qubit-based synchronization method, we perform a demonstration in a four-state RFID system and show in the figure. Our method is successful in able security distribution over the fiber link extend up to the 200 kilometer. This represents the longest experimental transmission distance achieved today for a few state RFID system. And the last, let's summarize our work. In this work, we have first we propose a four-state RFI QKD protocol that can construct a passive measurement RFID system, and then based on the four-state RFID system, we introduce a machine learning-based synchronization method that used for time-based RFID system, and successfully eliminate the need of additional synchronization hardware. And finally, the system can successfully enable security key distribution over the fiber channel extending up to 200 kilometers. And of course, although this method demonstrated stable operation in the optical fiber link, but when in free space with the temper influence, this method should be more this method should be further investigation, and this is also the future we were to research. And in our method, this method will use some qubit for synchronization, so it will 就是it affect the quantum the key rate is also a problem for the future should to research. And the last, finally, still, thanks for my supervisors Shi Hai Sun, Ke Jingwei, and my colleagues. That's all. Thank you.
Thank you for the talk. It's time for questions. Right. Any questions?
Thank you for the talk. Did you do finite key analysis or only infinite asymptotic analysis yet? Or it's not yet a focus of your
you say the
yes. The question is about the last point in the third point in the conclusion. So
you say the
so it enables secure key distribution for up to 200 kilometers. So does it take into account finite key effects as well?
Yes, it's
Okay.
consider the finite key. And this is the experimental result. Is also the finite key is considered about it's about the system is 100 is the system is one frequency of 100 megahertz, and the date is the daytime is the sample time is the 1,000 second. We consider the final key.
Okay, thank you.
Thanks for the talk. So for your machine learning algorithm, is it being done on the fly, like real time, or is upon the, or is it some kind of post processing?
就是 in this method,就是 due to the time being based is time window is more complicated than the B based 4. So the machine learning is to classify the different detection from the different time windows, and then so we can successful achieve the periodic cover. Use the same method in the B based 4 that we proposed.
Okay, maybe I'll
machine
catch up
learning is
again later. Yeah.
used to classify the detection events into their different time windows.
Okay. Yeah, thanks.
Okay. One more question there.
All right, thanks for the talk. Can I ask, when you're using the machine learning protocol in order to do this resynchronization, how much data do you actually need before you can do the reconstruction? And does this kind of have any limits when you go to really high loss, where you might have fewer events to actually do the reconstruction?
In our system 就是the losses is can 就是let me see the experiment result. The fiber is about 200 kilometer, and the loss is the the 40 dB, and then 就是 and then the loss is can more higher, but the protocol is security is only in this. This method can achieve in a higher loss channel. It can do this.
Okay, last question over there.
Thank you so much for the talk. My question is actually really simple one. Sorry if I missed, but when you test the QBER and secure curate, which data did you use to transfer? Like, did you use real-time generated pseudorandom, or did you use prepared pseudorandom bits, array of bits, and you repeated it?
The qubit is let me think. So in our experiment, the qubit is for the experiment state and about 1,000 second, and the encoding is used about the random bit that are used for the QAD protocol. And the synchronization bit is not considered in the qubit. It's different.
Okay, I think